In this lesson we're going to look at reversible reactions. Now the sign staring you in the face at the moment is the sign used to depict a reaction that is reversible. And a reaction that is reversible is one which can go in either direction. So for example, let's say we've got two substances reacting, A and B, and they react to form new substances C and D. Okay, so in a reversible reaction, what can then happen is that the products of the reaction, in this case C and D, can then react with themselves to reform the reactants A and B. So let's just make a quick note of that. Okay, so the products of the reaction react with themselves to reform the reactants. So we have two reactions going on at the same time. We have a forward reaction, and at the same time that the forward reaction is taking place, there is also a reverse reaction, sometimes known as a back reaction. Okay, so you've got the forward reaction, reverse reaction, both reactions taking place at the same time. So it isn't like, first of all, A reacts with B and then sometime later C reacts with D. These two reactions are going on simultaneously. Okay, so let's just have a look at a couple of very simple examples. First of all, the thermal decomposition of hydrated copper-2 sulfate. This is hardly really a chemical reaction in a sense, really it's a physical process because we've got water of crystallization which is incorporated into the structure of the copper sulfate crystal. And that's what gives the copper sulfate crystal this blue color. So when we heat this hydrated copper sulfate crystal, what happens is the water is driven out of the crystalline structure. It turns into a white crystalline substance which is the anhydrous. So we've got, I'll just write hydrated copper-2 sulfate, you know that bit, and anhydrous. Those are the words. Anhydrous means without water, hydrated means with water, and so the water's been driven out. So here it is, here's the 5H2O here. Okay, what will then happen is that the anhydrous copper-2 sulfate will also react with water to reabsorb it into its structure. So this is actually happening simultaneously while the crystal is being heated. Okay, and we'll talk about equilibrium in a minute. The tendency is for the reaction to go to the right, as being the forward reaction is taking place. So we say the forward reaction is favoured. That's because we're heating the hydrated copper sulfate. Once we remove that heat, then the reverse reaction is favoured, and the copper sulfate will then reabsorb water into its structure and reacquire the blue colour. So if I remove the heat, after a certain period of time, the white anhydrous crystals will return to the blue hydrated copper sulfate crystals. Another example of a reversible reaction which is quite often quoted in textbooks, and this is the decomposition of ammonium chloride. And ammonium chloride is a white crystalline substance, and so we're heating it here in a test tube, in a Pyrex test tube, and what's going to happen is that when we heat it, the ammonium chloride is going to decompose into two gases. One of those gases is ammonia and the other gas is hydrogen chloride. Okay, so you need to be careful when you're doing this because these are quite unpleasant and harmful gases, and so we're gently heating that. But what you're going to notice is that as you do so, and this is the important point, on the colder part of the test tube, okay, so here the test tube's hot, right, obviously because we're heating it, but up here by the mouth of the test tube it's cold, the glass is cold, and what's going to reappear again at the top of this test tube is the ammonium chloride. So the ammonium chloride, a white crystalline powder, is going to reform on the glass at the top of the test tube where it's cold. Okay, so where the test tube is hot, the forward reaction is favoured, that's to say the decomposition into ammonia and hydrogen chloride, but where the temperature cools down, where the glass is much cooler, the reverse reaction is favoured. So the ammonia gas and the hydrogen chloride react again with each other to reform ammonium chloride. So you get this white crystalline powder reforming on the inside of the test tube here at the mouth of the test tube. This is again a classic example of a reversible reaction. So we've got the reversible reaction sign here. So I just want to talk a little bit about the idea of equilibrium. As I mentioned earlier, what we have here is we've got our reaction, again A plus B forming C plus D, and this is taking place in what is called a closed system. What that means is that no material can enter or leave the system. As no matter can enter or leave. And what will happen eventually in any reversible reaction is that the reaction will reach a stage in which the relative proportions of A and B and C and D will remain unchanged. Okay, so we're reaching a position of stability, and this position of stability is known, as the title indicates, as dynamic equilibrium. Alright, so it's a position of stability where the amount of products and reactants present stops changing. That doesn't mean to say that the reaction has stopped. What that means, that when dynamic equilibrium is reached, what's happening is that the substances are still reacting with each other. A is still reacting with B and C is still reacting with D, but they're doing so at exactly the same rate. So the forward reaction is taking place at the same speed as the reverse reaction. So C is reacting with D with the same reaction rate as A is reacting with B, and the reaction reaches a stable point where the percentage of product and reactants is fixed. So you may, for example, have a situation where you've got 40% of A and B present and 60% of C and D. So in this particular case, the position of equilibrium, we can talk about the position of equilibrium, is shifted towards C and D. Okay, so what we're going to do in the next lesson is we're going to learn how we can shift the position of equilibrium. Okay, so in a particular industrial process, we may be interested in obtaining C and D. We don't want A and B, and that happens in lots of chemical reactions. So there are ways in which you can affect the conditions and the environment of the reaction to increase this percentage yield of C and D. So, by altering the conditions, and we'll look at those conditions in the next lesson, we may be able to increase the yield of C and D to 70%. So we'd have 70% C and D and 30% of A and B. Alright, so we'll look at that next lesson when we look at Le Chatelier's principle.